So this is ELC131, Circuit Analysis 1, and the topic of this video is the Superposition Theorem. Now, the Superposition Theorem states that the current through or the voltage across any component in a linear network is equal to the algebraic sum of the currents or voltages produced by each source acting independently. Now, if you've taken physics at college or in the college, you would be familiar with the superposition theorem. It's used to determine the effect of standing waves, where standing waves are either additive or subtractive. But in ELC 131, as we state here, the superposition theorem is used to analyze multi-source circuits. So the following procedure is used or followed to implement the superposition theorem. So step one, we replace all sources but one with their internal resistance. The internal resistance of a voltage source is 0 ohms or a short. The internal resistance of a current source is infinite ohms or an open. Step two, we determine the current through or the voltage across the component or components of concern. We need to denote the direction of current flow or the polarity of the voltage drop when we determine these currents or voltages. Step three, we repeat steps 1 and 2 for all remaining sources. And finally, step 4, we find the algebraic sum of the currents or voltages. So let's look at an example of the application of the superposition theorem. Now, understand that when we look at the circuit of figure 1, again, this is a multi-source circuit. We've got two DC sources, VS1 and VS2, applied to a series parallel combination of resistors. And of course, VS1 is going to supply some current. Some of it goes this way. However, some of it can go this way. And VS2 is going to supply some current. And this current can go this way. And of course, some of the current can go back in this direction. So because we've got two currents flowing through RL, we've got two currents flowing through R1, potentially two currents flowing through R2, we really don't know the direction of current ultimately through R1 and R2, but this circuit cannot be reduced using our typical or traditional circuit analysis reduction steps. Because there's two currents flowing through RL, there's potentially two currents flowing through R1 and R2. So we can't just reduce this circuit as we did in our analysis of series parallel circuits. We have to apply some circuit analysis theorem. Now we could make use of Thevenin's theorem or Norton's theorem, but again, for this video, we will show an application of the superposition theorem. So, first thing we're going to do is analyze the circuit to find VRL with VS1 acting independently. And you note in the circuit of figure 2 that VS2 is replaced with a short. So our resulting circuit places R2 and RL in parallel. And we've reduced the circuit of figure 2 to a simple series circuit by replacing RL in parallel with R2 with one equivalent resistance, shown as REQL, 2. And of course, we can find the voltage across RL. which equals the voltage across Req L, 2, using the voltage divider formula, Vs1 times R equivalent L2 over R1 plus R equivalent L2. And we result with a voltage across RL of 7.51 volts. Now, in this circuit, we need to keep track of the polarity of that voltage drop, positive to negative, because ultimately we're going to find the algebraic sum of the voltages across RL with each circuit acting independently. So again, looking at figure 2, the voltage drop across RL is positive to negative. Excuse me. So now we'll find the voltage across RL with Vs2 acting independently. And again, Vs1 is replaced with a short. And this places R1 in parallel with RL. And I've redrawn the circuit by combining R1 in parallel with RL into one equivalent resistor called REQL1 to derive a simple series circuit. And we can determine the voltage across the load, which is equal to the voltage across this equivalent resistance, REQL1, using the voltage divider formula, Vs2 times R equivalent L1 over R2 plus R equivalent L1, and we get a voltage of 4.37 volts. Now again, we have to denote the polarity of this voltage drop because we'll have to find the algebraic sum of these voltages. So the voltage dropped across RL in the circuit of figure 4 is positive to negative also. So the last step is to find the algebraic sum of the currents or voltages that we've determined with Vs1 acting independently and Vs2 acting independently. And again, both of these voltages were positive to negative, with Vs1 acting alone and positive to negative with Vs2 acting alone. So these two voltages, 7.51 volts and 4.37 volts, are additive. So the resulting voltage across RL is 11.9 volts. Now, you have to bear in mind that not all circuits are going to work out where these circuits are additive. For example, if Vs2 was had a polarity of negative to positive, then this voltage would not be positive to negative. This voltage would be, of course, negative to positive, and these voltages would subtract from one another instead of being additive. So it's important that when you find the voltages with each source acting independently, that you keep track of the polarity of these voltages so that we'll know whether they're additive or one subtracts from the other. So we'll make use of the superposition theorem when analyzing circuits that contain more than one voltage source. And again, this circuit could have been analyzed using Thevenin's theorem or Norton's theorem. However, a lot of students, a lot of technicians, a lot of engineers prefer to use the superposition theorem because it employs traditional circuit analysis techniques that we learned in the unit covering series parallel circuit analysis.